Back to tonight's lecture. Stephen Clifford was introduced to me by Jeffrey Briggs, who's with me here. Jeffrey Briggs was director of NASA's Solar Exploration Program in the 80s and director for the Center of Mars Exploration at the NASA Ames Research Center in the 90s. He now lives in Bath and has contributed a number of articles to our journal. Stephen Clifford, who he introduced to me, is a senior research scientist with the Planetary Science Institute in Flagstaff, Arizona, where he conducts research on the hydrologic and climatic behavior of water on Mars. Let me hand you over to Stephen Clifford.
Well, good evening. As Tony said, tonight's talk is going to center on the inventory of water on Mars and how it may have been cycled early in the planet's history and contributed to the persistence of the Northern Ocean. Now, why are we concerned about water on Mars? Well, there are a number of reasons. Its abundance and distribution have important implications for the evolution of the planet's surface, atmosphere, and climate. Its presence is vital to the origin and continued survival of life, and it represents an invaluable resource for sustaining future human explorers. Now, I've stolen a slide from Michael Carr's presentation last fall because it provides a much more efficient summary of the present conditions on Mars than my slides did. Because Mars orbits at a distance from the sun that is 50% greater than the Earth, Mars is a lot colder than the Earth. Mean annual temperatures at the equator are around -60 degrees centigrade, and at the poles are -120 degrees centigrade. Because Mars has a spin axis, which is tilted roughly the same amount as the Earth's spin axis, about 25 degrees, Mars experiences seasons as it orbits the sun. The atmosphere is thin, less than 1% of the Earth's atmospheric pressure at sea level, and it is composed predominantly of carbon dioxide with small trace amounts of water vapor. Another important factor is that Mars is much smaller than the Earth, about 1/10 of the mass of the Earth, and its surface gravity is about 1/3 of the Earth's. Now, the first close-up views we had of Mars came from the Mariner 4 flyby mission in 1965. And for someone who was growing up, read the stories of Arthur C. Clarke and Robert Heinlein, the pictures that we got back from this flyby mission were a little disappointing. Instead of canals and domed cities, what we saw was intensely cratered terrains that looked very much like the moon. And for people who were hoping to find evidence of life on Mars, this was extremely discouraging because it made Mars seem like the moon, that it was dry and lifeless. However, over the succeeding missions to Mars, our perspective on the planet, on its geologic evolution and on the abundance of water changed significantly. The earlier flyby missions that followed Mariner 4, Mariner 6, and 7, unfortunately passed by the same areas, heavily cratered areas of Mars in the southern hemisphere. But when we finally sent orbital spacecraft to Mars, the Mariner 9 mission in 1971 and the Viking mission in 1976, we were able to get a global perspective of the nature of the geology on Mars and the potential role of water in the evolution of its surface. Now, one of the most notable characteristics of Mars, this is a topographic map that shows that there are essentially two chief regions of Mars: the southern 2/3, the southern highlands, which are intensely cratered, and the much less cratered northern plains. The difference in elevation between these two regions is about 5 kilometers. And the difference in the number of craters that we see, we think, or actually we know, is a reflection of their relative age. The Southern Highlands being more intensely cratered and therefore being older than the Northern Plains. Now, at one time, we expect that the Northern Plains were just as heavily cratered as the Southern Highlands. However, erosional and depositional processes that occurred in the time since the Southern Highlands were formed have erased much of that early cratering record in the Northern Plains and buried it under deposits of sediments and lavas. Other features that you'll note are a large volcanic province, which is topographically high. This is an area called the Tharsis Bulge, and includes the largest volcano in the solar system, Olympus Mons, which would cover a basal area equivalent to the size of France and rises about 27 kilometers above the planet's mean elevation. There are also large impact basins like Hellas, which has a diameter of about 2,500 kilometers and a depth of as much as 9 kilometers below the global mean. Our gyre, a more heavily eroded but smaller impact basin that's about 1,200 kilometers in diameter, and a great equatorial canyon called Valles Marineris that would span from Los Angeles to Boston if you superimposed it on a map of the US, and in places as much as 500 kilometers wide and 8 kilometers deep. Now, one feature that I'm going to go back here, the feature that I'm about to show you, which is called the valley networks of Mars, are found throughout the Southern Highlands. So they're found throughout the oldest of terrains of Mars and are absent in the northern lowlands and in any of the younger volcanic plains that exist around the Tharsis volcanoes. This indicates that these features date back to a period of around 4 billion years ago, and again are noticeably absent from terrains that are younger than 4 billion years. These features greatly resemble the kind of runoff features that we see on Earth that result from rainfall. Well, the atmosphere of Mars today is far too thin and the temperatures are far too cold for rain to have occurred. So the presence of these features throughout the heavily cratered terrain of Mars in the Southern Highlands suggests that the early climate of Mars was substantially different than the climate of today. And that, in fact, early Mars may have had a greenhouse climate, a much more massive atmosphere of CO2 that allowed temperatures to rise above freezing and allowed the occurrence of rainfall and liquid water to flow on the planet's surface. Now, again, the absence of these valley networks for terrains younger than about 4 to 3.7 billion years indicates that there was a transition from those early warm conditions to the conditions more characteristic of what we observe on Mars today at about that time, at about 3.7 to 4 billion years ago. Now, in addition to the valley networks, which again are found throughout the Southern Highlands, the other significant feature indicating the presence of large amounts of water on Mars are the Martian outflow channels. The majority of outflow channels are concentrated in the area north of Valles Marineris and along the eastern edge of Valles Marineris. And these are really massive erosional features, thousands of kilometers long, in many places as much as 100 kilometers wide and a kilometer deep. And it indicates that vast amounts of water were discharged on the surface to create this level of erosion. Here I've got a close-up on the left this region at the eastern end of Valles Marineris that shows a little bit more of the scale and extent of these features. And on the right, a close-up of a small region of this area that again drives home the enormous scale. I mean, this scale bar down here is 50 kilometers wide. And this is actually just a small portion of the area that shows clear evidence of fluvial erosion. Unlike the valley networks, which look like they were formed by precipitation, there are no integrated valleys in the regions around the occurrence of the outflow channels. Instead, these channels appear to have formed full-born from regions of disrupted and chaotic terrain. And what this suggests is that the water that created the channels actually burst out from the subsurface. And in the late 1970s, Michael Carr, who was the principal investigator on the Viking orbiter imaging team, proposed a mechanism for the origin of these outflow channels, where he noted that given the cold climatic conditions that existed at this time, which postdated the era in which we believe Mars may have had a more Earth-like climate, and was now in climate conditions that were more characteristic of what we observe on Mars today, that as a result, the near surface of Mars would have been frozen to considerable depth, and by considerable depth, on the order of 1 kilometer or more. And that this region of frozen ground would have acted as essentially an impermeable barrier and allowed this, the isolation of large volumes of groundwater in the southern highlands. Now, these regions of disrupted terrain that we see as sort of the birthplace of these massive outflow channels might then have been created by asteroid impacts, by earthquakes, or by magmatic intrusions that would have disrupted this cryosphere that would have provided the hydraulic seal, keeping the groundwater in the highlands and allowed that water to discharge out onto the surface. Now, in addition to the valley networks, we see in the highlands, the outflow channels that we see in the transition region between the highlands and the northern lowlands. We also see other features along the boundary between the highlands and the northern plains that have been interpreted as evidence of possible paleo shorelines that indicate that early Mars may have had an ocean that once covered as much as 1/3 of the planet's surface. I'm going to take a closer look at the geographic distribution of these paleo shorelines. This is a north polar projection of Mars, and it shows the dichotomy boundary where one set of potential shorelines have been identified. And if these are in fact shorelines, they appear to date back to the very earliest times in Martian geologic history. And then within that region, another set of fairly well-defined shorelines that there's a lot more agreement about are paleo shorelines that show much greater continuity and again, much more physical evidence of having been eroded by liquid water. Now, on the right, you see the kind of geomorphic evidence that's being cited to identify these shorelines. And in this left-hand image, you can make out very, very faint traces along the dichotomy boundary that Tim Parker, one of my colleagues at JPL, did identify as paleo shorelines. They are very subtle, and there are potentials for them being confused with other things like the contacts between successive lava flows or exposures of strata in the highlands. So the acceptance, let me just, no, okay. So the acceptance of these as indicators of an early ocean are still debated. And I'd say that there is still a significant fraction of the community which is skeptical, maybe as much as 30%. But I think the remainder of the community is pretty well convinced that at least very early in Martian geologic history, the planet did in fact host these expansive oceans in the northern plains. Now, if those oceans really did exist, they would have provided a ready source for the water that created the valley networks back 4 billion years ago. And here we see, this is essentially the outline of Contact 1, this largest ocean, which we believe would have dated back to the period about 4 billion years ago. And then Contact 2, which has a younger age, and either may represent the slow disappearance of a single ocean that lasted a long period of time on Mars, or may represent the episodic occurrence of an ocean where the early ocean had a greater area and the later ocean had a much smaller area as water from that ocean was cold trapped in the polar regions and into the thickening regions of frozen ground in the planet's crust. Now, if there were a long-term ocean in the northern plains, this was a period where there were a number of large impacts into the northern plains. And one consequence of those impacts into an ocean would have been the creation of tsunamis. On Earth, tsunamis produce very distinctive morphologies, lobate debris aprons that propagate upslope around the shores of an ocean and produce very, very distinctive landforms. The key observation is the fact that they propagate uphill. Normally, a debris flow you would expect to be transported down the topographic gradient. But along the dichotomy boundary, again, along the region where we see this evidence of paleo shorelines, we see these lobate deposits that propagate hundreds of kilometers past the dichotomy boundary and into the highlands. And about the only mechanism we can think of that could create these kind of features are tsunamis from large impacts that occurred in an ocean at that time. And over on the right, we see some evidence of these lobate debris flows that have propagated into the heavily dissected terrain along the dichotomy boundary. This is additional evidence located, we're looking at a region called Arabia Terra that's on the dichotomy boundary, where we see additional evidence of flows coming in from the northern plains that deformed around topographic obstacles. This is called fingerprint terrain, but again, is consistent with the idea that it was generated by large impacts, large tsunami deposits. Now, I've spoken about the evidence for past water on Mars. Now I'd like to talk about the inventory of water that we can actually see on Mars. And by far the largest reservoir of water that we can actually see are in the Martian permanent polar caps. There are seasonal caps that occur on Mars during the winter months when carbon dioxide condenses out onto the surface. And those seasonal caps can extend down to latitudes of 45 degrees or so. But in the spring and summer months, those seasonal polar caps of CO2 disappear and reveal residual ice caps made of water ice. In the North polar cap has a diameter of 1,000 kilometers and a central thickness that reaches 4 kilometers. In the South Polar region, the diameter of the South Polar cap is roughly 1,500 kilometers, and it reaches a central height of about 3.5 kilometers thick. Altogether, the amount of water that's contained in the polar caps is equivalent to a global layer of liquid averaged over the surface of Mars of about 25 meters deep, which is a significant amount, but nowhere near the amount that is implied by the erosion associated with the outflow channels or the occurrence of a northern ocean. The other observable reservoir of water on Mars are water ice clouds. Here they're seen in a colorized Viking image around the largest volcano on Mars, Olympus Mons, that I spoke about earlier. But if you were to condense all the water in the Martian atmosphere onto the planet's surface, it would only form a layer 10 microns thick. That's about 1/10 the thickness of a human hair. So the amount of water contained in the atmosphere is actually very, very small. So how do we reconcile this with the estimates of the very large amounts of water on the planet earlier in its history? Well, estimates of the total inventory of water on Mars extrapolated from the amount necessary to erode the outflow channels fall in the range of a global layer of liquid 0.5 kilometer to 1 kilometer deep. So this is a massive amount of water. Of that amount, 1/1,000,000th of 1% is present currently in the Martian atmosphere, and about 5% in the Martian polar caps that we observe today. The remaining 95% has either been lost to space or is currently residing in the subsurface as ground ice, groundwater, or as hydrated minerals. So the question is, how did Mars evolve from this very water-rich planet early in its history to the planet that we see today? Well, one possibility is that during the transition, the climatic transition back 4 to 3.7 billion years ago, Mars lost a good deal of water. During this time, prior to 3.7 billion years ago, we know that the sun was in a very active phase where it had a solar wind. These are particles of electrons, protons, and alpha particles that are streaming out of the upper atmosphere of the sun that was likely 100 times greater than it is in the present day. And the impact of that solar wind on a planetary atmosphere has the ability to erode that atmosphere over time. And since the flux of this solar wind was so much more intense back at this time, Mars could have lost a considerable amount of water, and it might well explain the loss in the massive atmosphere that would have been required to produce a greenhouse and the transition to conditions like we observe on Mars today. But this really doesn't explain the conflict between our estimates of the abundance of water on Mars early on in its history and the lack of water today, because those estimates are based on primarily the erosion associated with Martian outflow channels. And this was an estimate that was made by Michael Carr back in the 1980s based on his analysis of Viking orbiter images. And again, his estimate at that time on the amount of water required to produce that level of erosion was on the order of 50 meters in terms of a 50-meter global equivalent layer. And that he argued that that would represent maybe 10% of the Martian surface. And that if you looked at the amount of water contained globally on Mars, that it would be 10 times larger than that. So on the order of about 500 to as much as a 1,000-meter global equivalent layer. Now that's assuming that water carried the maximum sediment load when it discharged to the northern plains. In reality, on the Earth, we see sediment loads for catastrophic floods that are actually much less than that, which implies that much more water was required to create the kind of outflow channel features that we now see. So this is, I believe, a conservative estimate in terms of what the inventory of water was in this time period that extended from roughly 3.5 billion years to as recently as 2 billion years. So that suggests that the large fraction of that inventory of water that was responsible for the outflow channels might still exist on Mars, stored in the subsurface. And if that's true, this is a pole-to-pole cross-section of the Martian crust that illustrates how that water might have been distributed. And you've got this, because of the cold temperatures on the surface and because of the decline of geothermal heat flow over time, that the thickness of frozen ground in the present day could be on the order of 12 kilometers at the poles and maybe 3 to 5 kilometers at the equator. And that difference is because the mean annual temperatures at the poles are 60 degrees centigrade colder than they are at the equator. So you need, so the region of frozen ground would have been proportionately less. Now, that region of frozen ground would have acted as a tremendous sink for water. But if the inventory of water exceeded the ground ice capacity of that region of frozen ground, then any remaining water would have existed or would exist as a liquid where it would have permeated the lowermost porous regions of the crust. So essentially, we have two regions that are potential reservoirs of water in the subsurface: a near surface region of frozen ground that follows the topography, and a deeper region of subpermafrost groundwater. Another possibility is that some of the water that was on the surface of Mars, sorry about that, some of the water on the surface of Mars back at the time there was a northern ocean, and at the time these outflow channels occurred, some of it may have frozen in place and become buried under aeolian sediments, volcanic ash, and fluvial sediments, and preserved over Martian geologic time. So the northern plains of Mars may have significant reservoirs of massive ground ice buried under these sediments and volcanic ash layers. And this is just another cross-section of the crust going from the highlands on the left to the North Polar Cap on the right, showing how this complicated geologic evolution of fluvial discharges to the northern plains and the occurrence of flood volcanism, volcanic ash deposition, aeolian dust. Mars experiences large dust storms, and a lot of that dust gets transported all over the planet's surface. So you can have this very, very complicated stratigraphy of ice and lithic materials in the northern plains. Well, is there any evidence that the northern plains are really that ice rich? And in fact, there is. In 2003, the European Space Agency sent a spacecraft called Mars Express go in orbit around Mars that had a radar sounder. Now, the purpose of this radar sounder, because it was operating at frequencies that could actually penetrate the surface of Mars and theoretically propagate down to depths where groundwater might exist, was to map the distribution of water and ice in the subsurface. Well, it turned out that the characteristics, the electromagnetic characteristics of the Martian crust are such that this radar was not able to penetrate down to the depths where we think liquid water exists, but it was able to sound the near surface of Mars. And you get radar reflections from the surface when you get the strong contrast in electromagnetic properties between the planet's atmosphere and the rocky crust. You get less strong reflections from the surface when, instead of solid rock, the radar waves encounter highly porous materials like aeolian or fluvial sediments. You also get a weak reflection from the surface if there's a very large ice content in the shallow subsurface. And when we take a look at the radar results over in the left image, again, this is a north polar projection, we see that there's a distinct difference between the kind of radar returns we got from the southern highlands, which you see in the red colors, which indicates a strong reflection, and in the northern plains, where you see the blue colors, which indicates a very weak reflection. So the question is, does this represent just highly porous sediments that have been deposited in the northern plains? Or is this evidence of a large volumetric content of water ice? And one way we can distinguish between these two possibilities is to take a look at the kind of craters that occur on Mars. In many regions, we have craters that look very much like the craters that we see on the moon. And this is the kind of crater you might get if you took a BB gun and fired it into a pan of powder. It looks like the ejecta around these craters was ballistically emplaced. So individual particles that get thrown up above the crater and then are ballistically emplaced around the crater in a progressively thinning ejecta deposit. However, on Mars, and particularly in the northern plains, we see a very different kind of crater ejecta morphology, a lobate crater ejecta morphology, as if the ejecta was in place not ballistically, but flowed out onto the surface. And you see these lobate flows, which are similar to the kind of lobate patterns that we saw resulting from a tsunami in the northern plains. In addition, sort of confirming the role of water in this, you also see drainage channels emanating from these ejecta deposits, which again provide support that this unusual kind of crater morphology results from an impact into a water or ice-rich crust. And that's what we believe. And if you look at these purple dots, this indicates the distribution of these kind of craters in the northern plains and supports the belief that the weak radar reflections that we're getting from the northern plains results from the occurrence of ground ice. Now, again, I mentioned that this interpretation of a northern ocean is not universally accepted. The identity and continuity of the proposed shorelines as water-related landforms has been questioned. The mineralogy of the ejecta excavated by large impacts in the northern plains shows only modest evidence of aqueous alteration. And an early long-lived ocean is difficult to reconcile with existing climate models, which suggests that any ocean would have frozen and sublimed away in a geologically short period of time. Now, if the larger area of paleo shorelines that have been identified along the dichotomy boundary is an indication of what the extent of an ocean in the northern plains was 4 billion years ago. The inner paleo shorelines that have been identified appear to date back to as recently as 3 billion years. So this indicates a fairly prolonged existence on the planet's surface, much longer than can be explained by the transition into the kind of climatic conditions we observe on the planet today. So in order to address this long-lived northern ocean, my co-investigators and I have done some modeling and looked at some of the observational data to try and better understand the early hydrologic evolution of the planet during this period from about 4 billion years up to about 3 billion years. Now, again, we start 4 billion years ago, before the climate transition has occurred, with conditions that are like what we observe on the Earth today, where there were temperatures above freezing and where rainfall could have occurred and where water could have existed in an ocean and the northern plains, similar to the kind of oceans and seas we have on Earth. Now, at the same time, the amount of geothermal heat that was being radiated by the planet was at its peak. Early on, the concentration of radioactive elements in the crust was high, and that concentration has decayed with time. And one of the consequences of the decay of those radioactive elements is the production of heat. So the heat flow of the planet is thought to have declined with time as well. So what would have the consequences have been with this thermal evolution, the transition in climate and the decline in internal heat flow in terms of the hydrology of Mars? And this is a sketch illustrating what we think may have happened. At time equals 0, when the climate was more Earth-like, we've got rainfall, just like as occurs on present-day Earth. Some of that rain would have flowed on the surface and creating things like the valley networks. Some amount of that rain would have actually infiltrated the surface and replenished a groundwater table at depth. After the transition to colder climatic conditions and the decline in planetary heat flow, a freezing front would have developed in the near surface that propagated downward with time as the crust experienced additional cooling from the change in the climatic conditions and the decline in internal heat flow. And that region of frozen ground would have acted as a thermodynamic sink for both water in the atmosphere and water in the subsurface, and would have effectively sealed the subsurface from any further atmospheric resupply. Excuse me for just a second. I've got to get a drink of water. Thank you. Now in time T2a, we see how the distribution of water would have been affected later in the planet's history and could be characteristic of what the distribution of water is on Mars today if it had a large initial inventory of water, where you would have had a very thick region of frozen ground, again, extending many kilometers in depth, under which there exists a subpermafrost groundwater system. On the right-hand side, we see another possibility, and that is that if the initial inventory was on the smaller side of what we think existed back at the 4 billion years ago, that with time, all of the water on the subsurface may have been cold trapped into this thickening region of frozen ground, and that no groundwater survives to the present day. So these are the two possibilities that we believe may occur on Mars today. But let's go back to this period 4 billion years ago, when the climate has just transitioned to a sub-freezing climate from the more Earth-like conditions that we believe existed prior to 4 billion years ago. If there was a northern ocean, it would have become ice-covered. Within the southern highlands, this is an illustration that goes from the South Pole to the North Pole on the right. The southern highlands, obviously, on the left, the northern plains with an ocean on the right. But with the transition to colder temperatures, again, this freezing front would have developed in the southern highlands that began to cut off communication between the deep subsurface and the Martian atmosphere. The next stage in the evolution is as climatic conditions became closer to those that we observe on Mars today, is that ice would have become unstable at equatorial latitudes. Currently, I pointed out that Mars has polar caps at very high latitudes, and that's because the temperatures are cold enough for ice to stay in equilibrium with the water vapor content of the atmosphere. However, at equatorial latitudes, which are 60 degrees warmer, any ice exposed at the surface will sublime, and that ice will then be transported to the planet's dominant cold traps, the polar caps, through the Martian atmosphere. And you begin to get the creation of polar caps both in the south and in the north. Now, one consequence of this is demonstrated or illustrated in the figure on the right. Before the deposition of any water that originated from the ice deposits associated with a northern ocean occurred in the South Polar region, you would have had this region of frozen ground where essentially the temperature profile of the ground was in equilibrium with the colder temperatures in the atmosphere and the warmer temperatures due to the decay of radioactive nuclides at depth. And at this time, because the heat flow was higher, this region of frozen ground may have been on the order of hundreds of meters or maybe a kilometer. But then you deposit material that is sublimed away from the Northern Ocean and deposit it in the North Polar region. And suddenly you have an additional layer of insulation, which is going to change the thermal profile of the South Polar region, such that the melting isotherm, that is the depth at which temperatures get above freezing on Mars, will have been exceeded when you consider both the thickness of the cryosphere and the thickness of the polar deposits. And as a result, that melting isotherm will rise in the cryosphere and melt any intervening ice that was stored in that region of frozen ground. And if you continue this process, you can eventually get to a situation where the thickness of the polar deposits become great enough for the melting isotherm to intrude onto the actual base of the deposits. And from that point on, anytime any additional material is deposited on the top of the ice cap, an equivalent amount will be melted from the base. Now, the infiltration of this meltwater to the groundwater table creates a groundwater mound. It elevates the groundwater table beneath the region of basal melting. And the creation of that mound results in driving the flow of groundwater away from the poles towards lower latitudes. And in fact, we see evidence that this kind of basal melting actually took place. We see paleopolar deposits that indicate that 3.5 to 4 billion years ago, the polar caps of Mars were much more extensive than they are today. And this is a diagram showing the extent of those paleopolar deposits around the present day polar deposits of Mars. And in association with the perimeter of those paleopolar deposits, we see large drainage channels. But those aren't the only evidence of basal melting. We also see within the region occupied by the paleopolar deposits features that resemble terrestrial eskers. These eskers, an example of the Martian eskers, are seen on the left. Terrestrial eskers form when terrestrial ice sheets at their base reach the melting point, and the resulting liquid water flows out onto the surface carrying sediments and creates these inverted features that outline the path of where water came out to the surface. So these are essentially subsurface channels. And we see these features in association with large ice sheets that have occurred on the Earth. We see them in Canada and elsewhere that were once covered by massive ice sheets. And we also have identified similar kinds of features in Greenland and the Antarctic, where we know that there are subglacial lakes and network of subglacial rivers that extend out to the periphery of the ice cap. And we think that Mars at this time, 4 billion years ago to maybe 3.5 billion years ago, experienced the same kind of activity. Mars, like the Earth, is thought to have a very permeable and porous crust that extends down to considerable depth. It experienced similar evolution in terms of impacts, volcanism, tectonism, weathering, and various aeolian and fluvial processes that have created a very thick permeable layer that could extend down to as deep as 26 or 27 kilometers below the Martian surface. So this would have been an excellent medium for the occurrence of groundwater and for the transport of groundwater. Well, I've talked about how the initial evolution of the Martian cryosphere would have been the initial development of a freezing front in the southern highlands and the occurrence of an ice-covered ocean in the northern plains. But as time went on and those cold temperatures continued and the geothermal heat flow from the planet continued to decline, more of the ice that was present on the surface, relic of an early ocean or from some of these outflow channels that formed later in the planet's history, would have been transported into the polar regions and introduced via basal melting into the subsurface. But at the same time, the region of frozen ground, this cryosphere, would have been getting thicker. And whereas the early cryosphere would have been too thin to have supported an elevated water table in the northern plains, in the southern highlands, as the cryosphere thickened with time, it would have eventually allowed the occurrence of an elevated water table in the southern highlands, and thus explain how water that may have once been associated with the occurrence of a northern ocean could have been introduced into the subsurface, sequestered by the presence of a thick cryosphere in the southern highlands, and then later released as massive outflow discharges, again, by impacts or earthquakes or igneous intrusions that may have then disrupted that hydraulic seal of frozen ground. Now, in this analysis, I've projected things as essentially being fairly constant in time in terms of the climatic conditions. And in fact, there's evidence that the axial inclination of Mars has varied with time, going from essentially zero, where the spin axis was perpendicular to the orbital plane, to an inclination as high as 60 degrees. Now, when the inclination was 0 degrees, when the spin axis was perpendicular to the orbital plane, that would have been when the poles were their coldest. However, when the spin axis is inclined by 60 degrees, the polar regions, in fact, get so warm that they're no longer the preferential cold traps for water, and water migrates from the polar regions closer to the equator and condenses on places like that Tharsis Bulge where the Tharsis volcanoes occur. We think, in fact, that these times of high obliquities that you get very significant ice sheets that form over this region. So again, the surface conditions have not been constant with time, and we wanted to also take a look at how that variation in axial inclination, which occurs on a time scale of about 120,000 years, how that may have affected the evolution of the Martian hydrosphere. Again, this is just an illustration showing what happens in terms of the redistribution of ice to lower latitudes when you do have these high obliquity excursions running anywhere from 35 to as much as 60 degrees, with the redistribution of ice to lower latitudes. Okay, to get a better understanding of this, my co-investigators and I have attempted to simulate the entire hydrologic cycle of early Mars. And to do that, we've combined three different models: a global climate model that simulates the transport of water through the atmosphere and to the polar regions, an ice sheet development model that looks how the deposition of water in the polar regions results in the formation of large ice sheets and the potential occurrence of basal melting, and then a model of subpermafrost groundwater flow, how the formation in response to basal melting of a groundwater mound drives the flow of groundwater away from the poles to lower latitudes. The climate conditions that we examined were obliquities of 5, 15, 25, and 35 degrees. And we did that because these are the obliquities where the poles are the dominant sink for any water that passes through the atmosphere. We also looked at atmospheric pressures of 1 bar, essentially equivalent to what we have on the Earth today, half a bar and a tenth of a bar, to look at what the impact was of this transition from a warm early climate to the kind of climate conditions we observe on Mars today. The ice sheet model is one that's based on a model of terrestrial ice sheets that's been very good at predicting the growth and behavior of ice sheets in the Antarctic and Greenland. And it takes into account inputs from the global climate model, as well as our knowledge of ice physics in terms of the conductivity of the ice, the flow laws for the deformation of ice, and our understanding of what the heat flow of Mars has been over geologic history, to come up with estimates of the extent and thickness of a Martian ice sheet at this time, its glacial flow velocities, basal temperatures, and basal melting rates. And again, over the history of Mars, we expect that the heat flow of the planet has declined considerably. And to look at what the consequences of that decline in heat flow was, we looked at heat flows of 65 milliwatts per meter squared, which is roughly 3 times what we believe the present heat flow of Mars is, 55 milliwatts per meter squared, and 45 milliwatts per meter squared. So we're looking at this period in the transition of Mars from warm early conditions to the colder conditions that we observe today. Now, we did this analysis for a variety of polar inventories of ice equivalent to a 500-meter global equivalent layer and a 200-meter global equivalent layer, with these 3 different values of heat flow that would have reflected the very earliest kind of heat flow we expect on Mars, sort of an intermediate value, and a value that begins to approach the value we think that characterizes Mars in the present day. Actually, the present day heat flow of Mars has been estimated to be on the order of 25 to 30 milliwatts per meter squared. And we looked at what the combination of these 2 factors, the size of the inventory of water and the geothermal heat flow, would have been under conditions of a 1 bar atmosphere and a 25 bar obliquity. And what we found is that for the larger inventory of water on Mars, there would have been an enormous amount of basal melting that would have occurred. And the basal melting in this diagram, this is again a polar perspective of Mars, where the colors in red indicate the regions where basal melting is occurring. And the regions in blue are where there's essentially no basal melting occurring. And we see that for the highest heat flows, there is a tremendous amount of melting that it's actually occurring at the periphery of the cap. There's some in the central portion of the cap, but with this much water and this kind of heat flow, the cap is deforming. And in addition to the geothermal input of heat, you're also getting sliding friction that results in the melting of a significant amount of ice. And you get as much as 6.5 cubic kilometers of ice that is melted each year, in the equivalent of almost 4.5 kilometers global equivalent layer that's cycled through the atmosphere, the polar cap, and the deep subsurface over a period of 10 to the 8th years. At 55 milliwatts per meter squared, you still have significant amounts of melting, but not quite as great as you do earlier in the planet's history. And then at 45 milliwatts per meter squared, with a 500 meter inventory of polar ice, you still get fairly substantial amounts of melting occurring. However, if you go down to a smaller inventory, 200 meters, the amount of melting that occurs is much less. For early in the planet's history, maybe on the order of 1.5 cubic kilometers of ice melted each year, or the equivalent of 700-meter layer of water averaged over the planet's surface cycle in 100 million years. And progressively smaller amounts as the geothermal heat flow of the planet declines. It turns out that the amount of meltwater produced by this large inventory is so great that it's no longer geologically reasonable. We don't observe the level of erosion that we would have expected from this very large inventory. So it suggests that the polar inventory during this period of time was actually much smaller, on the order of about 200-meter global equivalent layer. This shows not only the effect of heat flow, but the effect of obliquity. And we see that when the obliquity is low, the amount of meltwater produced is less. And that, again, is because of the cold polar temperatures at low obliquity. And that at high obliquities of 25 and 35 degrees, we get significantly more basal meltwater that's produced. Well, now incorporating this into the groundwater flow model, this model is based on a model developed by the US Geologic Survey that's been very good in predicting groundwater flow on Earth. And we've applied it to the Mars, given the kind of conditions that I previously described in terms of heat flow and surface temperatures and the occurrence of basal melting. And what, again, we see is that over time, basal melting results in the growth of a groundwater mound beneath the polar cap that can drive the flow of groundwater to lower latitudes. I've taken an extreme example, the 500-meter global equivalent layer, just to show the association of the regions of basal melting with the effect that it has on the groundwater table. And we see in the region where there's the most intense basal melting, you've got the highest elevation of the groundwater table due to the infiltration of basal meltwater. And in these other regions where there is also some significant infiltration of basal meltwater, you also get an elevated water table. Now, as you look at the evolution of this system over time, because the obliquity is varying on a time scale of 120,000 years, and because that means that the input of basal meltwater is varying over this time, you get pulses of replenishment that occurs to the groundwater system on a 120,000 year cycle as you go from very cold, low obliquity conditions to very warm, higher obliquity conditions. And our modeling suggests that this produces pulses of water that expand outward from the pole and propagate out towards the northern plains, where they could have replenished an early Martian ocean. And as you investigate how this system would have evolved over time, you go from a situation before any active basal melting has occurred, that we see here at time equals 0, to a later time after a lot of the water that's associated with the northern plains had been transported to the polar regions and resulted in basal melting, where you're beginning to get the rise of the water table in the southern highlands, to a point much later in the evolution of the Martian hydrologic cycle, where the groundwater table rises to a significant elevation in the southern highlands and is confined by the occurrence of a global cryosphere. And in this way, we believe we have explained the origin of the high water tables that ultimately led to the formation of the outflow channels later in the planet's history. Again, we think an ocean may have existed on Mars anywhere from the earliest times, 4.5 billion years ago, up to as recently as 3 billion years ago. The outflow channels seem to have occurred in a time frame from roughly 3 billion years ago to maybe as recently as 1 billion years ago. And with that, I'd like to summarize. The geologic evidence suggests that Mars has a planetary inventory of water equivalent to a global layer of liquid half to a full kilometer deep. About 3 to 4 billion years ago, much of this water may have resided in a northern ocean covering as much as a third of the planet. The presence of the valley networks throughout the planet's oldest terrain suggests that early Mars had a warmer Earth-like climate that approximately 3.7 to 4 billion years ago underwent a transition from the more arid and to the more arid and colder conditions we observe today. Following this transition, the introduction of water into the subsurface by cold trapping at the poles and basal melting could well explain the persistence of a northern ocean in the elevated groundwater table that led to the later formation of the outflow channels. And I think I've gone considerably over my time. And at this point, if you have any questions, I'd be happy to answer them.
Right. Would you like to unshare your screen then, and then we can see?
Sure.
But thank you. It's been definitely worth every minute of it.
Let's see. Okay. Took a while for me to find the right page.
Right. Well, we have one questioner in the chat channel at the moment. That's Charles Draper. Would you like to ask your question, Charles?
Sure. I actually have 2 questions, Tony. Is that allowed?
Yeah. Well, given there are no other questions at the moment, yes.
Okay. Stephen, can I say first, thank you for an amazingly sophisticated analysis of the various effects you're talking about in terms of what you can see and how you can try and interpret that, and how you try and dig deeper to try and understand it. And my brain is still trying to grapple with all that, but I'm so impressed by the way I put it all together. My questions are sort of 2 background ones that reflect my ignorance, I guess. And the first one is, why is it that the actual surface of the northern plains are so much lower than the southern uplands? What caused that?
Well, that's a good question. And if you'd like, I can either wait for your second question or answer that first one.
Well, the second question is quite short as well, so I'll give you the second one as well, a different one. I mean, I've been hearing stories about the northern polar caps of Mars and how much water is there for more decades than I care to admit, and I hadn't picked up that so much water is still there. So if there's so much water is still there, it might only be sort of 5% of what was there, but still a lot of water. Why aren't there attempts being made for a lander down on them to take a closer look at the water and see what it tells us?
Well, another good question.
Sorry.
Let me address the first one in terms of the explanation behind the origin of the global dichotomy, why the northern plains are as low as they are. And one suggestion has been that early in the planet's development, it was hit by another large protoplanet that caused a massive impact in what's now the northern plains. And the northern plains are essentially the relic of that early massive impact. Others have embellished that explanation a bit and say, well, rather than one large impact, there were many large impacts that occurred in the northern plains, and it's their combined effect that produced the low elevation of the northern plains. Those explanations are probably the dominant ones, the most accepted ones with regard to Mars today. There had been earlier suggestions that Mars underwent a catastrophic core formation event where there was a large, not hydrothermal, but a large convective cell that developed within the planet as the core formed, and that this eroded the base of the northern hemisphere of Mars and caused the crust to subside. That explanation doesn't seem to have held up over time. There have been a number of objections that have been made to that. One of them being is that we have evidence that early Mars had a significant magnetic field back prior to 4 billion years ago. And that suggests that Mars already had a fairly well established core at this time. Oh. Now, your second question was, why haven't we gone on and explored the polar regions? Yeah. Yeah. And that's an excellent question, because the polar regions provide the best evidence for climate change that we have over the course of Martian geologic history. The polar deposits in the south are thought to date back, again, billions of years. The polar deposits in the north appear to be more recent. And I think the oldest age that's been identified there is maybe on the order of 100,000 to 1 million years. But we see distinct layering in exposures and scarp faces in the polar layered deposits that we believe are a record of these variations in axial inclination that have occurred over time. Yeah. And one of the ideas that was proposed early on is that we land a rover on top of the cap and take it down one of the scarps in the polar caps and do drill analyses along the way to look at how the water and the sediments deposited in the polar ice varied over time and get a complete climatic record. Well, that was a little ambitious, but in the late 1990s, NASA actually did have a mission that it planned to send to the south polar cap of Mars. Unfortunately, there was a problem in the software, and the retro rockets were supposed to fire after the parachutes disengaged. Sorry about that. And due to a software error, they didn't go off in time, and the spacecraft plummeted to the surface and crashed. Since that time, we had one other mission, the Phoenix mission in the late 2000s, that was sent up to high latitudes, but not onto the polar caps. And it detected, it had a shovel that scraped away the surface and found ground ice very, very close to the surface. But certainly I and a number of other people would be very, very interested in sending a mission to the polar regions because of all the potential information that it could provide about at least the recent climatic history of Mars.
Yeah, sure. Okay, thank you. Thank you very much.
Sure.
We have a question from Chris Bullen. Would you like to unmute and ask your question directly? Well,
I think I'm getting there.
Right, okay.
Okay, I'm intrigued that the northern area seems to have far less topography. So, and I guess that's the reason why you're giving it an early age, because it doesn't have a cratering record. That raises the interesting question is, what is burying the topography to give you the early sedimentation? And what is the sedimentation? Because if it was derived from the erosion of the highlands, you would expect quite a low, and an ocean there, you would expect quite a low sedimentation rate in that ocean, in the floor of the ocean.
Yeah, again, a good question. And there are actually several things that may have contributed to the resurfacing of the northern plains. One of which is the fact that there may still be a substantial amount of the ice associated with the former existence of an ocean that froze in place and was subsequently buried by aeolian deposits, by fluvial deposits, and volcanic deposits. And over the period from 3 to the past 1 billion years, we may have had additional deposits of ice and sediment and volcanic ash and related things in the northern plains with the outflow channels, in association with the outflow channels. So there's this belief that there could be hundreds of meters of material that has now been deposited on the northern plains, and that there has also been, during this time period, at least when there was active fluvial activity occurring, the erosion of any impacts that had occurred in the northern plains. We see hints of large craters that whose rims just seem to be poking out of the northern plains. Looking at the laser altimetry data that we have for the northern plains, there are indications of buried craters in this region. So the estimate is that we could have deposits, both in terms of massive deposits of ice and volcanic and aeolian and fluvial deposits that could total hundreds of meters thick.
Thank you.
Sure.
Do you have any questions?
I need to think about those. Are very fascinating talks, Steve. I need to think about it, and questions that I come up with, I'll send you by email.
Sounds good.
Okay. A question I'd like to ask then is, what investigations of Mars would you like to see in the future, in the near future?
Well, I think the one I'd most like to see, and which I'm surprised hasn't been pursued more aggressively, is a geophysical and meteorological network mission. We've sent spacecraft to various regions on Mars, and we've sent some very expensive rovers to Mars, but they are necessarily limited to just the location around where they land. Even the Curiosity rover and the Perseverance rover on Mars that NASA has sent over the past few years have explored relatively little of the planet's surface. And I think one way to get a more comprehensive understanding of the planet's surface is to send a network mission where you send maybe 10 or 12 landers at one time, low-cost landers that would be equipped with both geophysical investigations and meteorological stations for us to get a better understanding of the meteorology of present-day Mars, which we know to a very minimal extent, and also the nature of the deep subsurface. Now, we did a few years ago send the InSight mission to Mars that consisted essentially of one seismometer. It also was supposed to carry a heat flow probe, but the Martian surface turned out to be a little bit more resistant to the penetration of that probe than we had thought, and so we didn't get any accurate heat flow measurements. But we have gotten some understanding of the seismicity of Mars, and the geophysicists who were involved in that mission have used an analysis of the seismic waves that we received to make interpretations about the nature of the crust and the mantle and the core of Mars. But if we sent 12 of these kind of landers across the planet's surface, we could obtain a much better understanding of the regional differences in things like the thickness of the crust, the depth of the mantle, the size of the core, whether groundwater was present at depth, the thickness of frozen ground. Not only with seismic techniques, but with electromagnetic techniques that would be very effective in looking at the distribution of groundwater. And with many more meteorological stations so that it would improve our understanding of the meteorology of Mars. So I think that that is where I wish we saw more emphasis. For essentially the cost of one of these huge rovers that we've sent on Mars, we could do a global investigation of Mars using both seismic and meteorological stations that would, I think, significantly improve our understanding of Mars. And each of these stations could be equipped with a simple camera system to give us an understanding of the landing site. So I think there's a lot of science that could be gained there. With the delay in the Mars sample return mission that NASA and ESA have recently announced, where we won't retrieve the samples obtained by the Perseverance rover until perhaps 2033, there is an opportunity to send lower cost missions like this until that sample return mission is ready. Another orbital mission that I'd like to see sent would be for a high frequency synthetic aperture radar. I mentioned the Marsis radar, which was tuned to provide a deep sounding understanding of the Martian crust. It was hoped it would tell us what the nature of the crust was down at many kilometers depth and whether groundwater resided at the planet. But as I mentioned earlier, the Martian crust turns out to be more attenuating to radar waves than we had originally thought. However, a high frequency radar that has the ability to sound down to a depth of maybe 5 meters or so in the Martian subsurface could tell us a lot. It could, for example, look at the layering that we observe in the polar caps that may have recently resulted from variations in the axial inclination of Mars, and give us a much better understanding of the properties of those layers, how much ice was deposited, how much dust was deposited in the layers. It might reveal valley networks that have since been buried since the time of their origin, have been buried under mantles of aeolian dust, and essentially peeled away any place where there is a near surface sedimentary layer that is obscuring older terrains, thus giving us a better understanding of what the distribution of rainfall might have been on early Mars back 4 billion years ago. So that also, I think, would be a good alternative mission to be looking at as we wait for the sample return missions to mature.
Thank you. Jeff, would you like to unmute and switch your camera on?
Right, yeah, I'd like to go off on a bit of a tangent. Everyone's interested in whether we can find any traces of life on Mars. And I was struck by the fact that that you said that Mars cooled and froze over so long ago, 3.7 billion years ago. Now, 3.7 billion years ago on Earth, there was no complex life forms at all. In fact, it took very much longer to really somewhere between 1 billion and 500 million years ago before complex life forms and plants evolved on Earth. And if Mars froze over so early, that suggests that there's very little possibility of complex life having ever evolved on Mars. I wonder if you have any thoughts about that.
I agree, and I think that most of the people in the astrobiology community would agree as well. Really, the question is, in the period in which Mars had more Earth-like conditions, had enough time transpired for very simple forms of life to evolve, and then adapt to essentially a subglacial or subterranean existence. You know, on Earth, we've got evidence of life in the deep subsurface of the Earth at depths of kilometers that have adapted to living off of nothing other than the mineral and constituents present with the presence of water and rocks in the deep subsurface. And it's possible that early Mars may have developed some simple microorganisms during this more clement period of Martian geologic history that were similarly able to adapt to a subterranean existence. And I think that that's the hope right now. There is at least some indication that may have actually occurred. One of the big surprises in our investigations of Mars in recent years has been the detection of methane in the atmosphere. The majority of methane in the Earth's atmosphere comes from biological activity. And it's possible that if Martian life did adapt to a subterranean existence, and they were methanogens like many of the subterranean organisms are on the Earth, that they would have resulted in the production of large amounts of methane that may have been incorporated into a region of frozen ground and produce things like methane hydrates, gas hydrates, like we find in the permafrost regions on the Earth. And that subsequent climate change has thawed some of that frozen ground and allowed methane to be released to the atmosphere. Another possibility is that tectonic activity has opened up fissures that have allowed communication between a deep subsurface biosphere on Mars and the atmosphere, and that has resulted in these releases of methane. But this methane that is released seems to disappear much quicker than we had expected. We had expected it to stick around for, maybe 100 years or more. But it seems that it disappears on a much faster time scale than that. So there are breakdown mechanisms, evidently, for methane in the atmosphere that have limited the amount of methane that we actually see.
Thank you.
Sure.
Well, we have a question from iPad. I'm guessing that's Deepali. Would you like to ask your question?
Oh, hello. Sorry, yeah, I didn't type in my name. My question really is, when you were talking about possible collection of samples of either soil or any objects from Mars to be brought back to Earth, my fear for humanity is that these potential presence of microorganisms could bring about disaster on Earth, because the atmosphere on Earth is so much more congenial to evolution of life forms and microorganisms that the less friendly atmosphere of Mars would have not allowed that evolution to take place over millennia, and then bringing it back to Earth could then create a sort of a crisis for humanity.
There is certainly that concern, and there have been a number of studies that have been done on potential ways of ensuring that kind of contamination from Mars doesn't occur. The capsules in which the samples of Mars are being encased in by the Perseverance rover have been studied for decades in terms of how to construct them in a way that, given any kind of conceivable mishap, would not release their contents to the Earth environment. that these samples would only be studied in the kind of labs here on Earth that we use to study, highly communicable diseases like Ebola. And it seems that within the biology community, that there is a fairly high level of confidence that the procedures that have been developed will be able to ensure the isolation of any potential Martian microbes. I actually have a reverse concern, and that is that a number of the spacecraft we've sent to Mars have not been cleaned to the point where we can't, where we can guarantee that there weren't any terrestrial microbes that hitched a ride. So far, the best we've done in cleaning a spacecraft were the Viking landers in 1976, which were subjected to very high heats that would have killed any terrestrial organisms. So we're fairly confident about these two landers that were sent there to look for evidence of life in the near surface of Mars, that they didn't contaminate Mars with terrestrial organisms. But there have been many other spacecraft, lander spacecraft, rovers that have been sent to Mars that have not been cleaned to that standard. And my concern is that terrestrial microbes that could potentially be introduced into a habitable environment. For example, we have over the past 20 years or so identified features on the surface of Mars that look like they are the result of the melting of near surface ice or the presence of near surface brines that potentially, if terrestrial organisms were introduced into these features, could represent environments in which these terrestrial organisms could reproduce. That has two downsides to it. One, it raises the possibility that if we detect life on Mars with our life detection experiments in future missions, that we may in fact be detecting life that we brought to Mars. The other possibility is more of an ethical concern. If Mars did develop a native biosphere that has survived 4.5 billion years, really, what right do we have to introduce terrestrial organisms that could potentially result in the destruction of that biosphere simply because we were so eager to find out whether life had evolved on Mars independent of the Earth? This was a question that was considered by Carl Sagan back in the 1960s. And it was his belief that if we did detect evidence of life on Mars, that it would put Mars off limits to any future human exploration, because the presence of humans on the Martian surface would inevitably contaminate the planet. So yes, there is this question of the potential contamination of the Earth from life that may have originated on Mars, but there's also the potential issue of life that exists on Earth potentially contaminating Mars. In fact, there's been some discussion that this may all be a moot question, that large impacts on both Mars and the Earth have succeeded in transporting material in both directions over the course of the geologic history of both planets. To date, we've found, I think, about 125 meteorites that we can conclusively identify originated from Mars. And we can do that based on their composition and the fact that we've measured the composition using the various landers and rovers that we have on Mars and can show that they're identical. So we know that Martian material has come to the Earth, and we've probably only detected a very small amount of it. Likewise, when you look at the orbital dynamics, the impact dynamics, we believe that a lot of ejecta from large Earth-size impacts may have been transported to Mars. So there may have been a cross-pollination that has occurred. And one of the things that's of interest to astrobiologists is to see if there is Martian life. Did it evolve independently of the Earth, or do we see a common origin? And this this is why the issue of the possible forward contamination of Mars, that is bringing terrestrial organisms on board terrestrial spacecraft, is such a concern. Because if we do find that life on Mars is similar to life on the Earth, then there's going to be some uncertainty as to whether we brought it there or whether it naturally existed in the Martian environment.
Well,
Thank you. Do you have any solutions?
Well, we've reached 9 o'clock now, so okay, yeah. If you want to say anything about that, that's fine. But I think we need to start drawing it to an end.
No, I think planetary science in general is characterized by the more we learn, the more questions we have. So no, I don't have the definitive answer to it. Certainly, it would have to be at least largely based on a genetic analysis of that life and whether there were significant differences between known terrestrial microorganisms and the organisms that we retrieved from Mars.
Thanks.
Well,
thank you.
We've had an absolutely great lecture this evening. I'm sort of trying to get my head around saline groundwater, cryospheres, frozen masses under the sedimentation and debris that might have landed on top of it, the interaction with the polar caps and so on, and above all, the sheer quantity of water that there may still be on Mars. I mean, this is a really exciting thing to consider. So what I would like you all to do is to unmute and let's have some applause for Stephen Clifford, please.
Thank you.
Thank you very much.
Thank you, Steve.
My pleasure. And Jeff, good to see you.
Likewise.
Again.